So I will mostly speak about eigenvalue problems and error control. And the focus is on a posteriori error control. So this is after computation, how can you certify the quality of your computation through computable. So I guess I don't need to tell to this crowd the importance of quantum mechanical models, but it's always very illustrative to look at these numbers. So here we have two keywords: Navier-Stokes equation, very traditional in applied mathematics, and the density functional theory. And I have here two columns. One is the number of hits on Google Scholar to represent the width in natural science of these key topics, and then its representative subset in mathematics. So okay, first surprise somehow, the DFT, you get about double of hits than Navier-Stokes. But then if you move to MathSciNet, you see there's a huge mismatch in terms of mathematical contribution to this field, which is quite important in terms of the whole Google Scholar metric in some sense. And further on, if you go on allocated CPU hours on supercomputing centers, you see that there's a huge part. Well, this is one example of the Swiss National Supercomputing Center, but I'm very certain if you go from one center to the other all around the globe, you see different numbers, but the main message will always remain the same, that chemistry, materials, some part of physics, they have a huge percentage in allocated CPU hours. All right. So, yeah. So here, that is the outline of today. So this is more a math-focused talk. So I give first some mathematical introduction to the Schrödinger eigenvalue problems, some families of nonlinear eigenvalue problems, including Kohn-Sham DFT. And then I first address the a posteriori error control in the density operator for linear problems. If you have any question, please just let me know in some form. I don't know what the usual procedure is for virtual talks, but please let me know. Then I will present some ideas to extend it to nonlinear problems before going to error estimation by perturbation theory. And if there's time remaining, I speak a bit about the Feshbach-Schur-based numerical method for plane wave discretization. So by the way, how much time do I have? Is it 1 hour plus 50 minutes discussion, or is it 1 hour and 15 minutes altogether?
I think we'll be doing 1 hour and 15 minutes plus some time for questions, but there might be some questions during the talk as well.
Okay, good. Perfect. All right, so let's start. Just to set the notation, let omega be a bounded or unbounded domain, and we denote by L2 the space of square integral functions on omega with inner product denoted by this notation and the norm correspondingly. Okay, then we focus on certain subspaces. This is here denoted by curly H, which is a subspace of H. This is a function that are L2 with gradients that are L2. And the character of this curly H is that it encodes the proper boundary conditions, so either homogeneous, periodic, or none, if it's an unbounded domain, in order somehow to cover a little bit everything, material science for crystalline structures, but also chemistry, which is on the unbounded domain. And it's not of great importance what this really is for this overview of the concepts. And then having set this space here, we look at the space, or more, it's not a space, a manifold of n tuples. So we have here n copies of this of elements in this space, but they're required to be L2 orthonormal mutually. So this I call curly M, and this is the infinite dimensional Stiefel manifold. Then you can define an energy, which in its generic form can be defined like this. And you look at the constrained energy minimization problem. I'm sure there were many talks about the formulation of DFT. And so this is one way of formulating it. So we minimize here, the constraints are directly embedded here in the energy, and here some class of functionals that can be described like this, for instance, LDA. All right. And so first remark, the energy as defined like this, in this way of writing a sum of contributions of the orbitals Vi, and here this terms only be dependent on the electronic density. You can show that the energy is invariant under a orthogonal or unitary, if complex valued functions are considered, transformation in the following sense. So we introduce here this notation. So phi is an element of the manifold here, and U phi for a orthogonal matrix here is to reshuffle all the orbitals by linear combinations of these entries Uij. So you kind of rotate the frames around, and so the energy is unchanged. Okay, that's an important remark for later. Secondly, let me specify a little bit on the boundary conditions. So for instance, for periodic cases, you can look at the potentials which are itself periodic on a bounded unit cell. And then this curly H is the subspace of H1 with periodic boundary conditions here indicated by the symbol here. Or you have simply homogeneous boundary conditions because you truncate your domain at a certain at the boundary, or even on the unbounded, if you have a potential that well, this should be actually 0, that goes to 0 as x tends to infinity. Okay, so what do you do with this constraint minimization problem? You can formulate the first order stationary conditions. So since you have constraints, you have to build the Lagrange, the Lagrangian, which consists of the energy minus all constraints times the Lagrange multiplier, which is encoded here in this lambda. So this should be a lambda here. So that is supposed to be a lambda, and the lambda is a symmetric matrix n times n, symmetric because otherwise you replicate here the conditions because this is a symmetric expression. All right. Good. Then what means stationarity? Stationarity means that if you take the derivative of the Lagrangian into directions, that this derivative needs to be 0. And we also know if we take the derivative of the Lagrangian with respect to the Lagrange multiplier, we recover the constraints here. So this is for granted by construction. And so the other interesting derivative is the derivative with respect to the orbitals here. Okay, and so you can do here the math, and then what you end up is an expression which is the derivative of the energy that is written like this. I will go into this in a moment, minus here this term here that comes from the derivation of the constraints here. This is not yet quite an eigenvalue problem, since for each phi I we test here with test functions here, but here we mix all possible or we have a sum over all possible other eigenfunctions. Okay, and so a rho here is an operator from H to its dual given by the following form. So it is minus the Laplace of phi times a potential that depends on rho, and rho is, as has been illustrated here, is the sum of the phi squares, and in this case, in Concham DFT is the electronic density. So this is the potential that has certainly a linear part and the also non-linear part applied to the function phi. So this is a multiplicative operator here. Okay, now since we have this invariance of the energy under orthogonal transformation, you can actually reshuffle your orbitals such that this expression gets diagonalized, and the condition that the derivative, the Gato derivative in all directions v is equal to 0 corresponds to the weak formulation of a nonlinear eigenvalue problem. It is nonlinear due to these red terms because the solution, the phi i's, built the row itself. Okay. All right. So here it is. So the question is, what is this operator here? We have introduced the operator without any power. So formally, you can introduce powers of operators in this way. But if we have an eigendecomposition of our space, and if you have eigenfunctions here, of the operator A, then we can take powers of the operator by scaling the eigenvalues here. And I highlight here in particular from the beginning, these are infinite dimensional Hilbert spaces. So H here, we are not yet in the discrete setting. H, this curly H is an infinite dimensional Hilbert space. So we get a countable set of eigenfunctions and eigenvalues. Okay. But I come to that in a minute. Okay, so for all the developments, we assume that the potential is regular enough such the expressions are well defined and that a row is self-adjoint and bounded below. Further, we are interested in the first n eigenvalues. So in order to decide what are the first n eigenvalues, you need a gap condition. Okay. So a few remarks. So the eigenfunctions are not unique, in particular for multiple eigenvalues. If you have multiple eigenvalue, you can turn your eigenfunctions as you want. And so also since the energy is invariant on the orthogonal transformation, the mathematical correct notion is indeed, or are indeed not the eigenfunctions, but rather the eigenspace that they span. Since once you have computed the solution, you get always the same energy, whether you turn that frame here with a U or not, you can generate in a whole family of solutions. So what is important is somehow the space of the functions they span. Okay, yeah. Good. So you can rewrite the weak form here in a strong form. And this looks like then this, the A operator applied to each phi I is equal to lambda I phi I. Okay. Good. So some examples. You can take as a row to be minus Laplace plus a nuclear potential. Maybe you want the pseudo potential, so this is pseudo potential. Then you have some can have some Coulomb energy and exchange correlation potential, and all this together, you have a linear part plus a nonlinear part makes this potential V, or sometimes it's also referred to the effective potential. But also you can put n equals to 1, and then you can cover in this framework also the Gauss-Pitayevsky equation, which is known to model Bose-Einstein condensates. And yeah, so you usually have a confining potential plus nonlinearity that it has some nonlinear strength, a beta parameter, and the row here, since we only have one orbital, is just the phi I square. Okay, so the Gauss-Pitayevsky is the mean field limit for bosonic systems at 0 temperature and some weak interactions. And then these solutions here, the phi i's, you can build a symmetric determinant in order to determine the wave function. Okay, so let us do a little glimpse on spectral theory, since I just by the sides use the notions. This is a self-adjoint operator with domain, the A bounded below, and with compact resolvent. So what does this really mean? So let us go a little bit into this, since this is a tutorial, I think that's useful, at least to address very quickly. All right. So what is the domain of an operator? A here, while here is all, I take here now L2 as the baseline Hilbert space, is all elements of L2 such as the image is also in L2. Okay, so basically all elements in L2 such that it makes sense to write AV. So it is bounded below is if I take all possible V's and test it with V and V, and I get something that is larger than or equal than a constant, which is finite. Good, so this clarifies domain and bounded below. Let us continue. So the self-adjointness is a bit more tricky because of the infinite dimension of the Hilbert space. The infinite dimension symmetric and self-adjointness is the same notion. For operators on infinite dimensional Hilbert space is a bit more tricky. So an operator is symmetric if you can put the operator on the other side for each u and v in the domain of A, and this more or less corresponds to the notion we have from symmetric operators on finite dimensional Hilbert spaces. So and symmetric matrices. Before we come to the self-adjointness, let us first introduce the adjoint operator. It has also a domain of definition and maps on L2, and it is defined by the mapping U to A star of U, where A star of U is this function that is uniquely determined as, so this is as Z, such that Vz is equal to AVU for any V in the A, and the corresponding domain for A star is exactly what I said, namely all U such there exists such an element with which this expression makes sense. Okay, and then self-adjointness is stronger than symmetric operator. So you first assume symmetric operator. This is equivalent to say that the domain of A is included in the domain of its adjoint operator, and then self-adjointness requires that the domains are actually the same. All right, so we have also clarified the notion of self-adjointness of an operator. And we come to the fact that there is a compact resolvent. So what is a compact operator? And the compact operator from, let's say here to Hilbert spaces, but it can be generalized from X to Y is a compact, or it is a compact operator if there exists a neighborhood U of the origin in X such that the image of U is included in a compact subset V of Y. So the image of a neighborhood is compact in Y. Okay, then the second term is resolvent. What is the resolvent of the operator? It is A minus Z identity and inverted. So this is the application Z to RZ A is the resolvent, and so the operator is with compact resolvent if this the resolvent is compact. Okay, so you kind of merge these two notions. All right, in this case, you know there exists a non-decreasing sequence of real numbers, the eigenvalues, that tend to infinity, and an orthonormal basis, phi k, consisting vectors of dA such that we have an eigendecomposition. And now, since the operator is bounded below, you can shift it to make it positive, such that all lambda k's becomes positive numbers. And with this at hand, you can, in the way I already introduced, you can define a to the 1/2, the operator 1 to the 1/2, by just taking square roots of the eigenvalues. These are now positive real numbers, and so this is the new operator, and its domain is actually all or is all V's such that this quantity is finite. That basically means we are allowed to write this expression. Okay. Yeah, and an alternative way here is to write A in this form. So you see, if I do a S here, I have a S here. That's a way to define fractional powers of operator. Okay. We have seen operators, so you can also formalize them in spaces. So first, we have this sigma 1 is a Banach space of traceless operators on L2. So these are our operators from L2 to L2. And it's given by the space of all operators that are linear operators from L2 to L2 with a certain norm that is finite. And the norm here is given by the trace of the absolute value of the operator, which is defined in this sense, for any orthonormal basis of L2 phi I here. And this is the analogon of the L1 space, but for operators, and you can have the L2 space is sigma 2, this the space of Hilbert-Schmidt operators on L2. And they have just a different norm. It is a Hilbert space, so there is a Hilbert. There's a scalar product between two operators. It's the trace between B dagger and C, and this is defined like this. And so this induces a norm to quantify operators. And you can write here the norm of B to be the infinite sum. So this series of B applied to each of the basis function. All right. Looking at the time, I skipped this. So let me come to the density operator. So as I said, we are looking for n orbitals or eigenfunctions, and I also argued that it's important to look at the space they generate, they span, and not necessarily at individual eigenfunctions. So this can be represented by the density operator, which is the operator takes a V, and gamma of V is then given as the scalar products between V and the functions times the functions, or more compactly written in the bracket notation in this form. Okay, and this is the density operator, and it somehow encodes, or it is isomorphic to the span of the eigenfunction you're looking at. Okay, it has some properties, nice properties. It is self-adjoint. It is a projector. It has a rank n, so the trace is n. And as well as the energy, it is invariant under orthogonal transformation. Okay, if I take a set of eigenfunctions, if I turn it by an orthogonal transformation, it generates the same density operator. So we therefore introduced here the infinite dimensional Grassmann manifold. So these are all operators in the sigma 2 that are self-adjoint projectors and of trace n. Okay. Let us return to the eigenvalue problem after this excursion to a little bit more of the functional analysis aspect. So the exact eigenvalue problem is not solvable on a computer simply because the dimension of the underlying Hilbert space is infinite dimensional. So you need to introduce a finite dimensional subspace, curly HH, and you can define the analogon of the Stiefel manifold, but for n tuples of your discrete space, and you still assume or want them to be orthonormal. Okay, so this is now the approximation space, and you can do the same business as before to find the first order optimality condition, etc., and you derive the analogon weak form of the eigenvalue problem. Where now here we have a nonlinear rho h, which is the built on the discrete orbitals. Okay, that's the same way. And in the same way, you can also define an approximate density operator through this bracket notation.
I have a question.
Yes.
Why in the weak form do you have the square roots of A? Why not just move the square root over to A?
Because then I have to write here a duality bracket. That's the simple. You could do that. So, but like this, we can interpret it as a scalar product in a Hilbert space. Yeah, you can move that, and then yeah, it's like the strong form versus the weak form, and you do an integration by parts. So whenever we have 1/2, you have to think about things like grad, and if we have a v u, it's kind of minus Laplace u times v. Okay. Okay. But the point is that if you have the Laplace of a function u that is in h minus 1/2, and the test function is in h1, and then here you have to interpret this as a duality pairing. Okay. Well, then going towards the implementation of this is now finite dimensional. This is a finite dimensional space, so you might want to implement you represent of the orbitals by a basis. So at this point, we need to introduce a basis, the size with any basis functions, and you represent each of the discrete orbitals as linear combinations. So with coefficients times the basis functions, and this ultimately defines the C matrix. Okay. Okay, so the eigenvalue problem is the nonlinear eigenvalue problem is equivalent to this nonlinear. Well, there's also eigenvalue problem, but what I meant by nonlinear eigenvalue problem was more this formulation is now equivalent to this form, which is in matrix terms that presumably you are all familiar with. Yeah, where you have the Fock or the Concham operator, and here this is the set of the eigenvectors. You have the overlap matrix, and here you build the density matrix that incorporates the nonlinearity in the Hamiltonian in here. Okay. This is solved mostly by self-consistent field iterations, meaning that you will start with some initial guess of the density matrix or not the full, but the diagonalization to get the first eigenstate here that maintain the orthonormality between the eigenfunctions, and then you build the new density matrix. So at each iteration, one needs to solve a linear eigenvalue problem. A good initial guess can drastically reduce the number of iterations, and it is common to use many kind of different acceleration techniques, and inversion in the iterative subspace, like DIIS or charge mixing, Pulley mixing, Anderson acceleration, and combinations of all this. Also, it is important to notice that many eigenvalues are solved. So this is proportional to the number of orbitals here, which is proportional to NB. Sorry, there's some typo here. Yeah, so the number of electrons is proportional to the number of atoms, and the number of basis functions is also proportional to the number of atoms. It's not just that the C matrix, you have many basis functions, but you also have an increasing number of eigenvectors to sort if you increase the system size. So therefore, depending on different properties, but you can have a computational complexity of this procedure up to n to the fourth. But many versions of codes have a lower exponent than this. Okay. Yeah. So this problem typically not only needs to be solved once, but many times if you do a molecular dynamics or geometry optimization. Now let us come back to the density matrix. So there's a direct link between the density matrix and the density operator through this relation here. And also the properties get nicely inherited. So we had the self-adjointness for the operator is now at least let's assume here we have a full real case, so no complex value function. Then we have a symmetric density matrix. It's a projection matrix. It has rank D, and it is invariant under a orthogonal transformation with a matrix U. All right. Where you can also introduce the Grassmann manifold. It's not exactly in terms of algebra the Grassmann manifold, but it's isomorphic to it. So here by Grassmann manifold, I call all NB by NB matrices that are symmetric, that are projectors, and that have rank n. And there's some nice things actually that since this is a differentiable manifold, you can at any point you can build the tangent space, and there's a mapping between the tangent space and the manifold. So the mapping from the tangent space here, a gamma vector down to the manifold, is called the Grassmann exponential, and the mapping from the manifolds to the tangent space is called the Grassmann logarithm, and they are locally around a point. They are locally bijective mapping. Some very nice feature is that if you take a t that goes from 0 to 1, so 0 times gamma is this point, the point where you build the tangent space, and t equals to 1 is here. So as t increases, you go here. Actually, if you take then the exponential function here, it parameterizes the geodesic linking the d with the d0. Yeah, I mean, find this beautiful. All right. Yeah. So, but this is not just an expression that comes from very pure algebra or Riemannian geometry. This is actually you can compute, and what you have to do is to compute an SVD. So if you want to compute the logarithm of a density matrix, what you have to do, and we assume that we build a tangent space at a certain d0. Yeah, so the d0 is represented by z0 transposed. What you have to do is to build this matrix and do an SVD. And with this ingredients from the SVD, you build this, and you have the logarithm. The other way around, if you want to compute the exponential of a gamma vector, you do first the SVD of the gamma vector, you build this C matrix, and then you build CCT. And the asymptotic cost is NB, so the number of basis functions, times the number of orbitals squared. But in practice, the pre-constant is quite low. So within, we observed that the pre-constant compared to other operation in a SCF iteration is really negligible. Okay. Let us come to a posterior error control for linear problems. So we now take the linear case. So A is here no longer dependent on the orbitals, but is some minus Laplace plus V. And so here we have the discrete setting. And for sake of being able to carry out the analysis, we assume the potential is L infinity. And we assume that the operator is bounded below by minus Laplace plus 1. So this means that the V is almost everywhere larger than 1. Okay, so And if V is just bounded below by a negative constant, you just add a constant. It doesn't change your eigenvalues. Okay. So the challenges are to deal with eigenvalue clusters and multiplicities. And this is one challenge. And the second challenge is you already see this, even if this is a linear eigenvalue problem, you have here a multiplication of two unknowns. That means you cannot exploit the linearity of this expression because this is not an expression that is linear in your unknowns. And this gives problems in the analysis that typically you would expect for nonlinear problems or nonlinear PDEs. So these are the challenges. And the question is, now we focused on the density matrices because we said the density matrix represent the space of the solution it spans, and the energy is invariant under a rotation of the frames anyway. So let's look at the spaces, and the spaces are represented by the density operators. And we have now two, an exact one, an approximate one. And how can you compare them and give error estimates? So in some sense, we are dealing with convergence of eigenspaces, how to quantify and estimate convergence of eigenspaces. And so this explains why I had to introduce also the Hilbert-Schmidt spaces, etc., because ultimately we want to have some kind of a norm to be able to compare different operators. Okay. So a few things about norm and equivalences. So assume we have some n functions in the Stiefel manifold. You can build this this is like a vector or vector of functions. You can build this norm as being just the sum of the individual L2 norms. You can do something similar if you put A1/2, and whenever you see A1/2, you have to think about H1 norm, okay? Because A somehow is like minus Laplace plus 1, so A1/2 is like the gradient of U in norm plus somehow the L2 norm. So this is the H1 norm. Or at least it can be bounded below by this, since we made this assumption that A is bounded below by minus Laplace plus 1. Okay, then you can relate the error in the orbitals here to the error in the density matrices. But here you cannot take an arbitrary, or you cannot take just well, I want this to compare with this, but I need to align the vectors, right? Because these are about spaces and projections, but I might have two different frames that are not aligned. So you have to align them with an optimization procedure, at least on paper. This is just for sake of analysis. You have to find, given a certain UH, and this is the exact one, you have to find a unitary transformation, orthogonal transformation, in order to best align the approximation with the exact vectors. And this is this quantity here. And if you have this, then this is comparable to the norm in the Hilbert-Schmidt space of the operators. And the same is for this H1 type of norm here. You can relate this up to some higher order terms to the H1 norm in terms of operators. Okay. So, but when you did the practical computation, what you're left with is the actual eigenvalues that you computed and the eigenfunctions in your discrete space. So what you start with is to build a residual. So the residual is a functional, so it's in the dual space, and you test it with a V, and this is nothing else than plugging in the exact formulation of the weak formulation, the residual of the weak formulation, for any v in the continuous space. And if this is 0, we know we have an eigenvalue and eigenfunction pair, and otherwise there's an error. Okay, but this is a residual for the orbitals and eigenvalues. But you can also define a residual for the approximated density matrix in this form, and you have the following relation that this kind of error quantity on the residual of density matrix can be approximated above by the element-wise residuals that you defined here. Okay, and then another lemma tells you that the error, so this is like the H1 error in the density matrices, can be bounded by the residual of the density matrix plus some higher order terms, and this one we already saw in the previous slide can be bounded by the sum of the individual residuals that you have here. Okay, so there you can substitute. So when substituting this in, well, this is higher term, you have to deal with it somehow. But the moral of the story is that you need to access the residuals in the dual norm. And for Fourier-based methods like plane wave methods, this is straightforward because you can access a norm in H-1 in dual norms, but it's very challenging, for instance, for finite element methods. Okay. So let us take an example. So omega is well, we just take plane waves basically. So you take plane waves of this form, complex exponentials, and you look at the reciprocal space. I kind of guess this is known to the public, so I'm rather quick on this. So we just look at plane waves for k vectors that lie within some ball of radius n. So this defines the approximation space. So then we have the following approximation or the following theorem. So what do we need? Let us assume we are targeting in our approximation the orbitals from index small n to index large n. And let us assume that there's a gap below, right here, and there's a gap above that is here. Okay, so this is straightforward in order that you can uniquely identify what is this portion of the spectrum. If you don't have a gap here, well, you have you're cutting in the middle of here, because here we're counting multiplicity. What is a bit more challenging is we need a lower bound of the n plus first eigenvalue, and this is this blue quantity here. And this needs to be a guaranteed lower bound of this one. Now this is known, and this is also computed, is also known. So this inequality can be checked once the quantities are known and defined. Then we have the following result, that the sum of the eigenvalue errors is bounded by some computable estimators eta square, and the H1 type error in the density matrix is bounded by eta. So as usual, you see double convergence for eigenvalues with respect to single convergence in the eigenfunctions. Okay, so what is this eta square? Eta square is some prefactor. You see here a 1 plus a pre-asymptotic term. Why is this pre-asymptotic? Because this is constant, this is a constant, this is constant, or converges to lambda n. So this is as a is stable. And this is the number of plane waves. So this is going to 0, this term. Okay. So the pre-asymptotic factor here is 1. And then here you have the sum of the residuals that you can actually compute in plane wave approximations. And this CH, this is a constant that you can actually compute because all ingredients are known. These are the discrete eigenvalues as well here, and here is this lower bound. All right, lower bounds also exist under additional miles assumptions, so that at least you know, the gamma applied on gamma h is not 0, so at least you get some of the eigenspace in your approximation. And this one, the way we do is, well, we look at the operator here that is strictly smaller, this one, and since we are on a rectangular domain, you know from the Fourier analysis, you know the eigenvalues of this operator, and this gives this bound. This doesn't need to be a very sharp bound as long as this is fulfilled, because it only appears here as a in the part which is asymptotically disappearing. So it doesn't degrade, it's not present in here. So how does this work? So this is a 2D, since all that matters in a posteriori error estimation is the regularity of the potential. We just give here the Fourier coefficients of the potential. This is not a meaningful potential, but we are interested here that there's a Coulomb type potential where you have 1 over k square. Okay, and then you can target different chunks of your spectrum, and we have different error quantities. So the error in the eigenvalue here, it's upper bound, and then the effectivity index, which is the ratio between the eigenbound and the error. And you see that this is converging nicely to 1, and the same for the this kind of error with the eta upper bound. However, we found out that it's quite sensitive to this alpha parameter. So it's just if you increase it slightly, yeah, the effectivity increases by at least an order of magnitude here. Yet there's still a strict upper bound, but yeah, that's the way it is. Of course, it looks more, it is more impressive here because you always have the doubling effect on eigenvalues. So if you look at the eigenvector error somehow, or this kind of error, is still mostly acceptable numbers. But usually you always have this term is the square of this, and whenever this is larger than 1, you get something that's even larger. Okay. Yeah, in finite elements, while looking at the time, I'm skipping finite elements. You can also do, but it's a bit more tricky. You need a technique that is called equilibrated flux reconstruction. You can estimate the residuals. That's the challenging term to estimate this, and you can do that with some computational bounds here. And I'm skipping this part. You have a similar result, and the point is, if you have elliptic regularity, then things are nice. If you don't have elliptic regularity, because, for instance, your domain is not convex, then you suffer as well. Okay, yeah. So, short summary at this point here. We derived here reliable and efficient a posteriori error estimates, or is at least possible to estimate the error in the density operator. So we look at the eigenspace and the error in eigenspace. It is asymptotically exact for plane wave discretizations and finite elements with elliptic regularity. The pre-asymptotic constant depends on the gap, and we also saw quite sensitive behavior on the amplitude of the potential. Okay, so this has been mostly reported in this article, which is kind of a succession of our first two contributions here. Okay. Let me present some ideas for nonlinear problems. But in this case, I focus on the Gross-Pitayevsky equation. So we have in general an energy functional that has a grad term here, a linear potential, and then here a nonlinearity, where here we take a convex function here, f, that is smooth enough. And so you look at the ground state, this problem here, and in the case of the Gross-Pitayevsky equation, is just f of v square is v square over 2, and you get this energy functional. All right. So again, you can look at the first order optimality condition as before, and in strong form, you find this problem where we now only look at one function and the smallest eigenvalue satisfying this eigenvalue problem. Okay, the weak formulation as before is here, then it is test function v, etc., blah, blah, blah. Okay, as before, you have to discretize it. I can be quite fast here. You have the weak formulation, the discrete weak formulation. And since this is also nonlinear, you have to solve it in an SCF-like fashion. So here the nonlinearity, you put an initial guess, you solve the eigenvalue problem, you update the nonlinearity, and you iterate. You can have a fixed approximation space, but you could potentially also have a sequence of approximation space that in the beginning is quite coarse, and only if you come close to convergence of the SCF, you start to add degrees of freedom. So this can potentially be a sequence of approximation space. Okay. Yeah. Now we would like to have error control of this, and we would like to distinguish between the error of the having not yet solved the nonlinearity and the error solution that comes from the fact that we only have a discrete space. And I explain you how we do that, and we need to speak now about the measure of the error. So now this part of the talk is not about the density matrices and the space, but it's about the energy. So it is a common choice for nonlinear problem to look at energy differences. So if your only goal is to have an accurate energy, then that's your quantity of interest. You want this to be as small as possible. What we do here is we augment the energy difference, this is the energy difference, with an additional term that is positive. Okay, so you can prove that this term here, at least for convex Fs, here that's a positive contribution. So you have the energy difference plus something else, and you see if U is V, then this term cancels and this term cancels. So whenever you have equal energy, this term is also 0. Okay. Then again, in the case of the Gross-Pitayevsky equation, well, this additional term is nothing else than u squared minus v squared squared. And it's obviously a positive contribution. Okay, you can introduce the bilinear form, where here the linearization is in blue, that's the first variable, and the eigenvalue is in red here, is the mu here. And without going too many details, this energy or this energy difference can now be represented in terms of a difference of bilinear forms. I don't want to too much address this, but we go now here. Now, you're at iteration I here. You have given the linearization. And now we look at the eigenvalue problem. but in the full space. So this is not a discrete space. And that's basically, we need this quantity, this green quantity. And this is, again, on paper, you can define it. In practice, you cannot compute it. But this is if you make the next SCF iteration in the full high-dimensional space, and this defines you this green quantity. So it is the exact ground state of the linearized problem around the current approximation. And since this is a linear eigenvalue problem, you can also represent it by a Rayleigh quotient, or by plugging in here, this is the Rayleigh quotient definition, since you have an inf. So this is larger than here testing with any W from your space. And let this guy be a lower bound, a guaranteed lower bound of this quantity. Then we use this because this is not accessible, but we have seen before we can estimate eigenvalues, and so we can potentially also estimate the lower bound of an exact one through the a posteriori error analysis we have seen in the first part. So then you can upper bound the error quantity, the augmented error quantity, by a computable quantity that is the actual eigenvalue at the iteration I minus this lower bound plus something that is fully computable. So there's only one constant involved, that is this guaranteed lower bound. Everything else is computable. Yeah. And we skip the proof. But then, in addition to that, this is this error quantity, this estimator. You can divide it in two estimators, a SCF estimator and a discretization estimator, in the sense that if you have fully converged the SCF, then this term is 0, and the error is guided or dominated by your discretization. On the other hand, if you have a very small discretization error, then this is very small, and this will be the dominating factor. Yeah. Okay. All right. What we have new is here this light blue contribution, where we add here and subtract here in order to distinguish, to have this separation in the two estimators. And this is actually the next eigenvalue you have in your SCF while maintaining the approximation space. Okay, and yeah, so this requires this further computation of this one and knowing this lower bound. And again, testing in the Fourier plane wave, you can now, for a fixed space, run the SCF iteration and monitor different quantities. So in black here, let me zoom in. In black here, that's the actual energy difference. Then this is the quantity we're going to estimate. This is squeezed in here. And then you have the total error, energy error estimator, the blue one here. And it can be written as the sum of the discretization plus the SCF. And you see in the beginning, let's say at 4 SCF iteration, you have a discretization error that is constant here. Why? Because your approximation space is fixed at all iterations. But you have a dominating SCF error, and this is here. This is given here by the magenta curve. And at some point, when the error here starts to be dominated by the discretization, then this becomes the dominant one, but the SCF still goes to 0 because you continue iterating. Yeah, that means at this point you should either stop your computation if you're happy with n equals 50, or if you want to reduce the error, then there's no point further doing SCF iterations because your error is dominated by the discretization error and you should increase your space. All right. Yeah, so here's just a zoom of this crossing over. Okay, so a short summary here. There is a generic a posteriori estimate has been established for rational approximation to some nonlinear Schrödinger eigenvalue problems. So they got Spitevsky type equations with one orbitals. So it involves only one constant, namely a lower bound of a linear eigenvalue problem. And this potentially can be estimated by the techniques of the first part of the talk. Okay, so in somehow this second part turns the problem of a nonlinear a posteriori estimation into the problem of a linear a posteriori estimation. Yeah, and this is the corresponding reference here. Okay, let me skip this one and maybe in the last 15 minutes to go quickly through something. That is based on the Feshbach-Schur map. So here. Oops, sorry. Okay. So now we're a bit leaving the a posteriori error setting, but we look at how to quantify changes of the eigenvalues and eigenfunctions through perturbation theory. And I'm not focusing on the traditional perturbation theory a la Schrödinger or that was formalized by Kato, but by means of the so-called Feshbach-Schur map. Okay, let me introduce that. Well, this is like more or less one slide here. So you have a Hamiltonian that is built by let's say a ground Hamiltonian that is self-adjoint, positive, and you focus on one isolated eigenvalue of some multiplicity m. And you have a perturbation that is symmetric and form-bounded, and so H is also self-adjoint. So form-bounded means that, or form-bounded with respect to H0, that this quantity is finite. Okay, now the theorem says that if this quantity here is smaller than something, so it's 1/2 gamma 0, and gamma 0 here is, if this is lambda star, you might have an eigenvalue here, let's call it I plus 1, maybe gamma I minus 1. So gamma star here is the min of the two gaps. Okay, it is the distance from gamma omega lambda star to the rest of the spectrum.
Hey Ben, can I ask a question?
Okay. Yes. Yes.
So isn't this form or form norm a little bit artificial in the sense that I can just add a shift to the H0 with an arbitrary large shift? This becomes small.
Okay, we do have a version where we add a H0, we add a alpha, but then I took this out, then you pay here for it. There's no free lunch.
That's because the lambda star gets shifted up too. You're dividing by lambda star. You're dividing by lambda star.
I can't hear it very clearly, but okay, you can in the H0, if you shift it, you shift also the H.
Yeah. So you shift H and what's wrong?
What is wrong? Yeah. The point is, well, you know, I took this out of the paper and I removed all the alphas, so I cannot plug it in quite easily. There we have a version where we shift. You have some alpha parameter where you can you can add an alpha to H0, because here we need to assume that this is a positive operator. And if you say, well, you can have this, you can eventually also shift something from below 0 to make it positive. And this makes sense to write. Okay, in order to have here the negative power, and here, yeah.
Yeah, I can see that in the asymptotic scaling is okay. If you shift at a arbitrarily in like a large alpha, it will to the leading order at least it will cancel. But after that, it seems to be still doing something, not just a multiplication. So the result, basically, what I'm saying is your result seems to depend on your shift. I just wonder whether there is a natural optimized parameter for the shift.
Yes, I mean the original version of the theorem is for some, you know, there's some result for some alphas that fulfill some criteria, and you as a user could then take or look for the optimal alpha. Yeah, but it is not straightforward that you can cheat to infinity by just lifting, and you don't have to pay for it. Yeah. Yeah, but for this discussion, it would be better to have the original version at hand.
Ben?
I simplified here for not making it too complicated.
Sorry, Ben?
Yes?
So when you shift it by alpha, doesn't the lambda star shift by alpha as well?
Yeah, that's the point.
That's the
yeah,
point.
that's the point. If it doesn't, then this thing will become too small.
Inequalities are also, that means that the potential has to be smaller as well. You only allow smaller potential.
More negative. That's right. Yeah. So yeah, when this becomes the alpha becomes too large, then to the zeroth order, there's no problem. But I cannot. It seems like it will depend on that shit.
There is an optimal alpha there.
Yeah, there is optimal.
Okay, thanks.
Okay, so I couldn't hear all the voices very clear, but yeah, there's an optimal alpha. Yeah. Okay, but this is just some kind of smallness condition, and as Lynn said, I mean, that's the that is the asymptotic estimate, and this is just automatically then fulfilled here due to this condition. But the estimate is basically this, that you control, of course, the variation of the eigenvalue from the unperturbed one by the perturbation. Okay, and so further, if you have an additional more restrictive condition, then you can also control the L2 norm of the unperturbed eigenvector with the, or eigenfunction with the perturbed one, and also possibly the H1 norm. Okay, so let us now go back to the linear eigenvalue problem of this form. And so here, this form boundedness, this can imply rather weak assumptions of on the potential V. So you want this to be finite for some positive R. And so if R is equal to 0, then this means it is Laplace bounded. And you have this embedding theorem. V is, if V is in HS, then it is this R has this R form boundedness property for R's satisfying this. Okay, this comes from Sobolev embeddings. But in general, it can be quite weak. So in cases where the variation analysis, at least where you can carry out on paper, the variation analysis of the plane wave method, this is included for S larger than D over 2, but you can have cases for less regular potentials where you still have a positive R here, but the variation analysis, at least on paper, doesn't hold. Okay, so what is the Feshbach-Schur idea? We define the orthogonal projector on the, let's say, plane wave basis or any discrete subspace Xn. And then you can define the best approximation. So phi n is not the variational approximation, but it's the projection. So this is the best approximation in your discrete space. And you can define the phi n perp. Okay, you can then obviously split the U into two components and then project your eigenvalue problem once with Pn to get this equation, and once with Pn perp to get the second equation. And so this is short notation. And well, then the sure part is that you want to condensate this equation in the first one. But in order to do so, you need an assumption that this term here, or this term is invertible. So under the assumption on V, you have that this is larger than some number that can be estimated here. And this depends on n. So in the case of plane wave approximations. And if you know that, then you can start to invert this. Because for any lambda that is smaller than the kappa n, you can invert this. So you have to choose n sufficiently large such that is larger than the lambda you're looking for. And the kappa n is a quantity that asymptotically, so this is n square here. There's some negative part, but this grows weaker than this one. So this is the leading one. It grows and grows. Okay. So once you know you can invert it, you can exactly do what I said. You can invert this part here and add it here. And then you can rewrite the Pn part here. This is just the part in Xn as a nonlinear eigenvalue problem with the Hamiltonian that is the projected one. So this is Pn H Pn, this Hn, plus a potential that depends on the eigenvalue you're looking for. And what I find fascinating is this is a nonlinear eigenvalue problem. And if you were able to solve it, you will get the exact eigenvalue, but it's an eigenvalue problem that is in Xn. Unfortunately, there's no free lunch. This potential, you know, it maps to Xn perp, that's an infinite dimensional space, and you have to invert an operator here. So this cannot be done, but what you can do is to say, okay, I have a slightly larger grid here with a parameter m, and I'm trying to invert this on this additional space here. So that's why we introduced this larger space xm. And also here, that is a resolution of a linear system. So you might use an iterative method and you do not solve this to full accuracy. Or in this framework of perturbation theory, you might also want to solve this by a truncated Neumann series, which in practice is equivalent to do a k steps or k+1 steps of a Jacobi type iterative solver. Anyways, but are the two approximations, is that you truncate this series here, the parameter k, and you solve the outer part only on this annulus.
Ben,
and
ask
yeah,
a question. Yeah, is there a version of this, a block version of this, when you need to deal with multiple eigenvalues that are clustered?
You can do this, in my opinion, in a straightforward way. Yes.
But each of this un depends on that lambda. right? So for each individual lambda, you need an individual correction.
You have to go through the density matrix again with the contour integral, in my opinion.
Okay, so there is a density matrix version.
Well, it's not. It's only in my head.
Oh. Okay.
Yeah.
That's hard to dig out. Okay.
But yeah, you can do that definitively. Okay. Yeah. So the approximation parameters is the n here, the m here, and the truncation of this Neumann series. Okay, and then you can solve this eigenvalue problem, and this is a problem in Xn. But in order to evaluate the potential here at a given sigma, you map somehow to the annulus, to this intermediate space. You invert it and you come back. Okay, and so you can have a similar, or there's this Fechbach-Schur estimates that pump in, and you can estimate the error in the eigenvalue here with a parameter epsilon that depends on those quantities here. And so what this means is that if the exact Hamiltonian has certain eigenvalues, the perturbation, so this picture applies to the abstract theorem I presented in the beginning. If you have a threefold eigenvalue in H0, the perturbation might split it because it breaks symmetry or whatever in 3 branches. And however, this is now a nonlinear eigenvalue problem. And this means, so if you consider this new I of lambda being lambda I, you can interpret this nonlinear problem as a fixed point. If the new i's are the eigenvalues of this Hamiltonian with the parameter lambda, so this means you have here this these crossings. These are the fixed points. That's the definition of these eigenvalues. Okay, so the definition of this, guys, you can interpret it as a fixed point, and this is the right-hand side, and this are these 3 lines. And as the perturbation becomes smaller, they collapse here to one point that is threefold. All right, there are some simple one-dimensional examples, but we also have 3-dimensional problems with a Coulomb singularity. The results are the same. So what you can do is you can take a fixed, let's say n equals to 2, and we take m large enough, and then you look how you take, you have convergence in K, because how to make this small? You have once a certain convergence rate in M, which is kind of the width of this outer layer. And if this is small enough, okay, when M is large enough, then you look at this part and you can reduce this either, if this is a number smaller than 1, by powers in K or by N. Okay, and so you see that here, that as you take different powers, you have this different decays. And but also if you go for fixed K, so you have a fixed K, but increase the N, then you also decrease. All right.
Can you remind me the relationship between L and N?
M and N?
No, L and N.
L?
Yes.
Where is L?
2 pi over L.
L is the box length. Sorry.
And how does it relate to N?
In the usual plane wave, well, N is increasing and L is fixed. And probably for this simple numerical example, we took it equal to 1. But as you discretize more and more, L is whatever it is. Okay? Okay. note also that the rate of convergence is the same for the eigenvalue and eigenfunction error. So that's obviously a drawback, because we know whenever we have a rational approximation, you expect the double of the eigenvalue. And by a triangle inequality argument, whenever you have a potential that is regular enough where you can apply the variational analysis, you can somehow in M, so this was the old epsilon, it has this one, you can substitute this with the variational estimates, and the epsilon tilde is now this part here. Okay, and then you in M you see the variational approximation errors, and this is what we observe numerically. So here, if S, so we took the limiting case, S equals 1/2. So here you have in the eigenvalue a rate of 2.5, and this is 3, so it is almost the same. So you see here's a slight difference here. But
Ben?
This is, yeah.
So we're a little bit over time.
Sorry? Oh yeah, we're
over time.
I'm coming to an end.
Okay.
Okay? And for non-regular potentials, you see a leading factor here that this term is actually here is given by this factor, but you don't have this kind of analysis here because you don't have enough regularity. So yeah, short summary, the approximation rates are similar for 3D problems. There's a new discretization method, and the analysis goes into regimes where the where for low regular potentials where the variation analysis does not hold, and extension to clusters of eigenvalues and nonlinear problems can be, or are based on contour integral formulations, can be imagined. So all in all, conclusion for linear eigenvalue problems, you can give complete a posteriori error analysis for plane wave methods and FEM for linear eigenvalue problems. You have gap dependency as usual in some of the constants. And for the nonlinear case, it's much less clear. One can also use perturbation-based estimates. That's the part I skipped. But I would also like to highlight the recent work by the French group on giving up a little bit of rigorosity and derive very practical and accurate bounds for plane wave DFT. Thank you for your attention.
Thank you.